If you type "Hello World" into a text editor, a computer has absolutely no idea what you mean. It only understands electrical signals, zeros and ones. So how do we bridge that gap? Unpacking the exact translation process between human text and machine action is one of the most common technical interview questions you will face. Welcome to Skip Uni. The journey starts with your source code. This is the human-readable text file where you write your instructions, saved with a .cpp extension. Look at this diagram. On the left, we have your clean .cpp script. On the right, the chaotic binary that the hardware actually runs. Bridging them is a conceptual black box where the translation happens. Knowing exactly what happens inside this box is the mental map you need to diagnose why a program fails to compile. Let's open it up. Inside the black box, the first discrete mechanism your code hits is called the preprocessor. The preprocessor is essentially a find and replace tool. It scans the code, strips out any human comments, and swaps out macro definitions, like turning a define pi tag directly into the number 3.14, before anything else happens. Once the text is cleaned up, the code moves to the compiler. Its primary job is rigorous error checking, scanning your logic line by line. It hunts for two specific issues. First, syntax errors, like forgetting a semicolon at the end of a line. Second, semantic errors, like trying to divide a number by 0. If your code clears these checks, the compiler generates a new encrypted block of data called an object file, saved with a .obj extension. This object file proves your logic is structurally sound, but it is incomplete. You cannot actually run this file yet. Think about commands you use to print text, like cout. Your .obj file knows you want to use it, but how does it find the underlying instructions to actually make it happen? This is where the linker steps in to resolve the missing logic. The linker connects your isolated object file to external libraries. In our printing example, it takes the definitions from the iStream library and snaps them directly into the empty slots of your code. By merging your source files with these external pieces, the linker produces a single, fully cohesive executable file, your .exe. The linker has taken a fragmented set of valid logical statements and transformed them into a fully self-contained, actionable program. There is one final friction point before we can see our code run: machine dependency. A Windows operating system expects that .exe file, but a Mac system expects a .out file. If you try to run your Windows executable on a Mac, the OS rejects it because the formats are incompatible. When you run the correct executable, it triggers the final execution step, and your output text is pushed directly to the screen. We've traced the entire path from text to action. Let's pull back and review the whole pipeline. This flowchart maps out the complete linear journey. You start with the .cpp source code. The preprocessor handles text directives. The compiler checks errors and outputs the object file. The linker connects libraries to create the executable, and the OS delivers the output. Memorize this sequence. When your code inevitably breaks in the future, knowing exactly which machine inside the pipeline is failing will be your ultimate diagnostic tool.